Thanks, the organizers, to give me the opportunity to speak. Today I recall about a new point of view for intrinsically Lipschitz graph in the Franchi-Serapione and Saracassano sense in metric spaces. First, I recall the motivation of my research, to find a good notion of rectifiability. Firstly, I recall the definition of intrinsically Lipschitz map in the Franchi-Serapione and Saracassano sense, and then I give the notion of intrinsically Lipschitz section in metric spaces. Finally, I give some properties and applications. The first question is, why do we study intrinsically Lipschitz maps? The answer is in order to establish a good notion of rectifiability in particular metric spaces called Carnot groups. As we know, a sub E, a subset of Rn, is countably derectifiable if it is possible to cover it with a countable union of the graph of Lipschitz functions. Ambrosio and Kirchen prove that this definition does not work in Carnot groups. So, Franchi-Serapione and Saracassano introduce a new notion of intrinsically Lipschitz maps in Carnot groups, which is our idea. They define suitable intrinsic cones, which are not equivalent to the Euclidean cones, and they say that a map 5 is intrinsically Lipschitz if for a point P belongs to the graph of 5, there exists an intrinsic cone such that the intersection between intrinsic cone and the graph is just the point P. In the picture, there is H1, the model case, the first Heisenberg group, which is R3, with the Campbell-Hausdorff formula. And in the red part, there is an example of intrinsic cone. In the blue part, there is an example of intrinsically Lipschitz map. My research, joint with Enrico Ledonne, is to generalize this definition in metric spaces. So, in Franchi-Serapione and Saracassano sense approach, they consider intrinsically Lipschitz maps. In our approach, we consider graphs. This is really important in order to generalize this definition in metric spaces. What is our setting? We consider X a metric space. So you have a set and you have a distance. Y is a topological space, so you have a set and you have a topology. And we consider pi from X to Y a quotient map, meaning continuous, open, and surjective. We say that phi from Y to X is an intrinsically Lipschitz section of pi if 5 is a section, that meaning that the equality 1 holds, meaning that the composition between pi and 5 is equal to the entity of Y, and the second inequality, inequality 2 holds. The second inequality, meaning that it is possible to compare 2 points, 5y1 and 5y2, with a point and a fiber. Pi minus 1 y2 is the set of a point x belongs to x, such that pi of x is equal to y2. In the picture, the fiber of y2 is the intersection between this red line with x, these 2 points, this and this. Because phi is a section, then pi is injective. Because of inequality 2, L is larger than 1 or equal, and the second inequality holds. That meaning that we study a sort of bi-Lipschitz condition. Behind intrinsically Lipschitz is equivalent as behind a bi-Lipschitz embedding when pi from X to Y is a submetry, meaning that it is possible to compare the ball. in the sense that the pi of the ball with center x is equal to the ball with center pi x, for all x belongs to x. Given x a point of the metric space x, and L is a number larger than or equal than 1, we define the set CXL, the set of all point x prime such that the inequality 2 is not true. So a section pi is intrinsically Lipschitz if and only if the intersection between CXL and phi y is in just empty set. We call phi y the graph of 5. In the Franchi Serapione and Serracassano definition, CXL is exactly the intrinsic cone. And here we have the graph of 5. In this sense, we call our approach, we consider the graph. Now I present an example. We consider X subset over 2 with the Euclidean distance. X is the union of A1, then the set over point X4, where X is a point between 0 and 1. A2 is in the set of all points X0, where X is between 0 and 1, and A3 is the set of all points 1x, where x is between 0 and 4. Y is the interval from 0 to 1. Pi is the projection map on the first component. That means that pi of A1 is equal to the x, pi of A2 is equal to the x, and pi of A3 is equal to 1. In this context, H fiber pi minus 1 y consists in 2 points, if y is not 1. The fiber of 1 is all A3. In this context, we consider 2 easy examples of intrinsically Lipschitz section of pi. F from y to A1, defined as Fy is equal to y4, and G from y to A2, defined as Gy is equal to y0. And this is 2 examples of intrinsically Lipschitz section of pi, where the constant is exactly 1. The properties of intrinsically Lipschitz section that we prove together with Enrico Redonne is the continuity, Ascoli-Arzela theorem, Alfors-David regularity, the link between the intrinsic Lipschitz section and the Lewis set of bi-Lipschitz maps, an extension theorem, a Leibniz type formula, and thanks to Chigger theory, we get an equivalence relation and we get a vector space over R. I focus my attention on Alfors-David regularity. More precisely, I recall our setting. X is a metric space, Y is a topological space, pi is a quotient map, and phi is an intrinsic Lipschitz section of pi. I recall the definition of Alfors-David regularity. Phi y is locally Alfors-David Q regular with respect to the measure mu, meaning that for each point x belongs to phi y, there exist 2 constants, R0 and C, not larger than 0, so that it is possible to compare the measure of the ball with R power Q, RQ. An additional hypothesis, we ask that there exists a measure mu on y, such that for every R0 larger than 0, and every couple point x and x prime with belongs to the same fiber, so pi x is equal to pi x prime, there exists C such that the measure of pi of the ball centered of x is less or equal to C the measure of the pi of the ball centered of x prime with the same radius r. Alford-Savid regularity says that if phi, the theorem says that if phi y is locally Alford-Savid Q regular with respect to the push forward of phi mu, then for any other intrinsically Lipschitz section psi, the set psi y is also locally Alford-Savid Q regular with respect to the push forward of psi on mu. Now I present the proof of this statement. I recall the hypothesis. We consider phi and psi two intrinsically Lipschitz section with the same L. Fix a point y belongs to y. And thanks to the Alford-Savid regularity of phi y, we know that the inequality for holds. Our thesis is to prove the same inequality for the case of psi. So we want to prove that inequality 5 holds. We use just 3 properties. We ask the fact that phi y and psi y belongs to the same fiber. That means that pi of phi y is equal to pi of psi y is equal to y. And we have this inequality. It is possible to compare the measure of pi of the same ball centered with phi y and psi y. The property B is just a definition of push forward. And C, it's an easy property of inclusion. Using these properties, it is possible to prove that push forward of psi mu of the ball centered of psi y and the radius r intersecting psi y is larger or equal than some suitable constant depends on C, L, and C1, and R power Q. Using the same properties, it is possible to prove the other inequalities. And so, putting together the last 2 inequalities, we have that the push forward of psi mu of the ball centered of psi y and radius r intersecting psi y, it is possible to compare this quantity with r power q. Thank you for the attention.